This tutorial is going to introduce the use of Stack Service, one of the service offerings of the Destination Earth Data Lake, DestinE Data Lake. What do we understand when we refer to Stack services? Stack can be summarized as a software as a service suite. These services are specifically tailored to enable near data processing, or often referred to as data proximate computing. The objective of near data processing is to move the computation to the data and not vice versa. This approach is depicted in the figure on the right. The advantage seen in near data processing is that data is processed where it is stored and only the result is transferred back to a central location. This is known as selective data transfer. Furthermore, analysis can always be executed on the latest data available, because of not relying on any data replication first. The Stack service offering shall support non-IT or cloud experts to interact with the DestinE Data Lake by providing applications that are already used for big data processing. The user community targeted by Stack service includes scientific programmers, data analysts, data scientists or scientists, etc. Most of the users in this community are using Python as their programming language of choice and make use of the Pangeo software stack to solve big data problems. Taking that into account, the DestinE Data Lake Stack service offering exposes fully managed services built on top of the Jupyter ecosystem, such as JupyterHub, JupyterLab, and Jupyter Enterprise Gateway. The Jupyter ecosystem is complemented by the Dask ecosystem, specifically Dask Gateway and the Dask Kubernetes backend. We will now switch into a browser to guide you through the DestinE Data Lake Stack service offering with a number of usage scenarios. Okay, let's try to log into the DestinE Data Lake Stack JupyterHub service. Therefore, go to the address shown on the screen. A login page will appear. Click the button Sign in with DestinE IDP to continue the authentication process. Destination Earth Data Lake is federated with the DestinE platform via which we will authenticate. Please provide your DESP username and password and press Sign in. After successful authentication, you will be redirected to JupyterHub. You can now select between different server options. The three last options will enable you to directly run a remote kernel on the given bridge, supporting the idea of data proximate computing in DestinE Data Lake. The use of these options will be covered in a separate video tutorial. For now, we'll focus on the option JupyterLab, full working environment. This option will spawn a JupyterLab at central site with ability to run your Jupyter notebooks. After the successful creation of the JupyterLab, you will be presented with the launcher window. The launcher provides access to two Python Jupyter kernels, a default kernel called Python 3 and a DestinE Data Lake specific kernel called Python DEDL. The Python DEDL kernel comes with pre-installed libraries to facilitate the interaction with other services. By selecting the kernel in the launcher, a new notebook will be created in your current working directory. This notebook is automatically connected to the DEDL kernel. Now let's close the notebook again and open a terminal window. As you can see, the home directory of the user is linked to the File Explorer in the JupyterLab, which allows for easy browsing in the file system. More advanced users can make use of the terminal to create new files or manipulate the directory content. Furthermore, the DEDL Python kernel is configured as default Python environment in the terminal. We can now list all the Python packages installed in this Conda environment. Specific packages such as the EarthKit, EC codes and EODAG packages are pre-installed to support the interaction with digital twin output data as available on the different bridges. Let's close the terminal and try to run some code in a notebook. Therefore, open again the untitled notebook we created before. Import NumPy and add some basic NumPy operations. The cell can be executed by hitting Shift-Enter. After successful execution of the cell, you will see the corresponding output of it. We can now rename the notebook by right-clicking and selecting Rename. Enter a new name of choice and hit Enter again to confirm. We want to run an example utilizing the other DestinE Data Lake services. A set of example notebooks is automatically cloned into your working directory every time you start a JupyterLab session. These examples you will find in the DestinE Data Lake lab directory. In there you will find example notebooks for the DestinE Data Lake Services HDA, also known as Harmonized Data Access, Hook, and Stack itself. We will now focus on a basic HDA example, showcasing data discovery and access via the HDA API. First we run some imports of needed libraries. After that we define some constants needed for the HDA API, such as the HDA API URL and other HTTP endpoints we want to use. We can now run our first request against the HDA API. We want to get all collections concerning chlorophyll A concentration and algal pigment. Executing the given code block will result in a JSON output indicating that 26 collections related to chlorophyll A concentration and algal pigment have been found. Individual collection metadata can be discovered via browsing through the output entries. Each collection holds a set of attributes such as the collection title, a unique identifier, and others. To finally access the data we have discovered, we have to authenticate again. Executing the given cell will provide us with input fields for our DESP username and password, which are finally used as authenticate header in subsequent requests against the HDA API. We want to get Sentinel-3 ULCI data for a given time range and specific region of interest in this example. When we run this query, we will see that 18 items have been found matching the given search criteria, with 3 items returned providing more details to interact with the data. With this information we can now start a download of a specific item. The item will be downloaded and stored in the current directory. The file name of the downloaded item will correspond to the ID of the item given in the search query. As you can see, the file appears after a few seconds in your directory for further use. So far we have seen how to run individual code in a notebook and provided examples. Now we want to reuse and clone a notebook which is hosted on GitHub. To do so, we browse to the GitHub repository holding notebook. To clone the Git repository, we select code and copy the HTTPS link provided. Now we switch back to JupyterLab and open the Git extension of it. Select Clone a repository and paste the link in the corresponding input field of the pop-up window. After clicking the Clone button, a new directory will appear in your work directory corresponding to the GitHub repository. You can now open the notebook in the repository and apply any changes as needed. Most likely such repositories come with a custom Python environment specification, like here, where a custom conda environment file is provided. Now we want to have a look into how to add a custom conda environment and kernel to your JupyterLab. To do so, we open a new terminal. We can now run the following command to create a new environment with Python version 3.12 installed called custom. We have to confirm with Y to install the environment. As soon as the new environment is installed, we can run conda activate custom to switch to the new environment. After activation of it, we have to install the IPython kernel library with. This can take a few seconds. To make the new environment available as a kernel in the JupyterLab, the kernel specifications have to be installed with the following command. Wait a couple of seconds and the new kernel will appear on the launcher screen. Now you can open a new notebook and run the following code in your custom environment to verify the successful installation. The new kernel will be persistent across sessions. If you would like to remove the kernel at some point in time, run the following command to do so. The kernel will disappear in the launcher. To uninstall the environment as well, run the following in the terminal. Now the kernel and the environment are again removed from your Jupyter Lab. As a next step, we show the integration of the DestinE Data Lake Stack services with the iLet storage service. First, we open the iLet storage dashboard, in this example the one provided by Lumi Bridge. We authenticate again with our Desk credentials and browse to the section Object Store. How to create a container or bucket is demonstrated in a separate tutorial for this service. We see that there are 4 buckets in total. The bucket called MyBucketLumi will be further used in the example, and we see that there is only one object stored. The Jupyter Lab contains an extension to which allows us to browse various S3 compatible object storage, such as the iLet storage service at Lumi Bridge. We enter the storage endpoint URL of the S3 service at Lumi as well as the access key and the secret access key we have received by the iLet storage service. Click Connect and the 4 buckets we have seen in the iLet storage service dashboard before will appear in the browser. We can also verify that the same objects are displayed as before by cross-checking the object in the MyBucketLumi. We are now going to switch back to the terminal to showcase how to access this bucket from the command line within the Jupyter Lab. Therefore, we will make use of the S3CMD tool which is pre-installed in the Jupyter Lab. Further details on how to configure the tool can be found on the respective documentation page provided by the DestinE Data Lake. For now, we assume this configuration was done already. We can now run to list all available buckets on Lumi Bridge. We get the same buckets as seen in the S3 browser before. Great! So let's move on. Okay, we want to upload some data to the MyBucketLumi bucket. First, we check the current objects in this bucket via we see the same object as before is visible. Now we are going to upload the Sentinel-3 file which we have downloaded before via HDA into this bucket by running the following command. This will upload the file to the object storage at Lumi Bridge. We can verify the upload via the Jupyter Lab S3 browser again. Great, we have been successful. If we want to remove the object again, we can do this by running Again, we can check the successful execution of the command by listing all the objects in the bucket or interactively via the S3 browser window in Jupyter Lab. This concludes the showcase on how to consume the iLet storage service via the Stack service JupyterHub, and we will continue with the Dask service offering of DestinE Data Lake. And now we are demonstrating the principles of data proximate computing by utilizing the DestinE Data Lake Stack service Dask. We will do that by making use of an example notebook available in the DestinE Data Lake Lab. Open the DestinE Data Lake Lab folder and browse to Stack and open the Stack Python client Dask notebook. This notebook gives a basic introduction to Dask and shows how multi-cloud processing with Dask can be done in DestinE Data Lake. The diagram presented here illustrates the high-level service architecture of the DestinE Data Lake Stack service Dask. 3 usage examples are depicted on how to consume the service. We will now focus on the scenario of user A in red. User A logs in into DestinE Data Lake Stack service JupyterHub and spawns a Jupyter Lab to run a notebook. User A wants to access data distributed across 3 locations, Lumi and Leonardo Bridge, as well as Central Site. Therefore, within the notebook 3 Dask clusters are created to consume the data on these locations directly to only transfer the final results computed near the data. This is showcased in the following. To access the service, a user needs to authenticate against the Destination Earth platform making use of their Desk username and password. Username and password needs to be entered in the corresponding input field and confirmed by pressing the Enter key for each input. After authentication, we can make use of the pre-installed DestinE client library, which allows for direct communication with various Dask clusters. The authentication object created before acts as input to this library. By utilizing this library, we are now spawning one cluster per bridge, as you can see in the provided output. We have now created 5 individual Dask clusters, which we will further utilize in the following. Running get cluster URL provides us with the URLs to the individual dashboard of the clusters to monitor the utilization of these compute resources. We can now open these dashboard by clicking the provided links. To confirm that all clusters are initiated, we can have a look on the given dashboards. We do see that each cluster has 2 workers assigned per default. A function is provided here to simulate computational load on the workers by just waiting for a second each time the function gets called. Now we want to apply myfunc on Leonardo bridge by providing an artificial file list called myFileListLeonardo and wait for the results to be returned. Let's see what is happening during the execution on Leonardo. Therefore we switch to the dashboard. We see that already all 3 workers picked up the tasks to be performed, 1 per element in the file list provided. After a few seconds all tasks are completed and we will switch back to the notebook. Now we are going to print the results and it looks as expected. We are now performing the same action on Lumi bridge with a different list of simulated input files. Again we can see in the dashboard of Dask how the works pick up the requested tasks for processing. We even see that 6 workers have been auto-scaled to complete the job. Printing the returned results in order to confirm the successful execution again. Great computation was done as expected for the 32 elements in the simulated file list. What are the limitations of this approach? The local and the remote Python environments have to match in terms of installed libraries and versions of it, and we can't share data between workers across bridges due to missing network connectivity. Okay, finally we are going to run through a use case example developed to show the advantages of this approach. The use case demonstrates the multi-cloud capabilities of DestinE Data Lake following the paradigm of data proximate computing, data of the Global Flood Monitoring (GFM) service as well as climate DT outputs, simulated by utilizing ERA 5 data are used for flood risk assessment. Data is stored as data cubes, ZAR format, at central site and at Lumi bridge in the DestinE Data Lake islet object storage. We access the data via the S3fs Python library in this example. We can now list objects in the increment 1 test data bucket and we will see 2 ZAR data stores in there. We want to read the data stored in S3 at central site. The data we want to read is a single ZAR data store, representing the GFM flood data over Pakistan for the 30th of August, 2022. After execution of these commands we see that we want to read in about 7 GB of data. Important to note is that we have assigned an attribute indicating the location of the data. Now we perform a simple calculation to compute the total area affected by the flood event. So far we haven't computed anything, so let's do the computation now on the Dask cluster. Let's run it on the cluster by firing these commands. We can again check the execution of the computation by monitoring the provided Dask dashboard. In this live view we see how Dask handles this workload by making use of autoscaling to speed up the computations. In total 10 workers are scaled out to perform the needed computation, and we are done already, so let's go back and check the result. We now see the computed flooded area displayed. So far so good, but how was that processing routed to central site? The method shown on the screen checks for annotations, attributes, in the given array and maps that to available Dask clusters. Let's do some additional computations. Now we want to run some processing on the data located at Lumi bridge. So let's load the data accordingly. We want to compute the accumulated rainfall based on the digital twin output simulated by ERA 5 data. Again, let's trigger the actual computation by running the .compute method. We do see in the Lumi dashboard that computations are carried out. Finally, we reproject the return results locally because the return data. We are now done with all the computations, therefore we want to shut down all the clusters spawned and free up these resources for others. We hope you enjoyed this tutorial on how to make use of Stack services in DestinE Data Lake. Please also check the other example notebooks provided to get more insights into the DestinE Data Lake service offering.